This lesson is all about solving right triangles. Let's start with the Pythagorean theorem, something you probably remember from high school geometry. My guess is you'll remember it as a squared plus b squared equals c squared. But we need to talk about what that actually means. The a squared plus b squared tells you to square the sides of a right triangle and add them together. They're going to equal the square of the hypotenuse. So the most important thing to do whenever setting up a problem is determine what the hypotenuse is. It'll always be located across from the 90-degree angle. So in our first example, the C is across from that angle. Let's go ahead and see the first example. RT is side C, so we're trying to find C. RS is 3 and ST is 4. So we're given A and B, and we have to find C. That means that A squared plus B squared equals C squared. Or 9 plus 16 equals C squared. To get C by itself without the square, we'll take the square root of both sides. I'm going to assume just the positive answer since we're working with distance. So C is equal to 5 in this example. For the next one, we're going to locate what the B value is, the ST side. RS is given as 6, and RT is 9. So it's important to note that the 9 side, the RT side, is the hypotenuse, which means when you set this up, I'll have 6 squared plus the unknown B squared equals 9 squared. Just do a little bit of arithmetic. I'll have to subtract 36 from both sides to get the B squared by itself, and then take the square root. I don't know what the square root of 45 is. It's not a perfect square, so instead we'll just use a decimal approximation for it. It's about 6.7. Next, let's look at an example problem. In this one, a ladder that's 12 feet long is leaning against a wall. The base of the ladder is 4 feet away from the wall, and we want to find out how far up the wall does the ladder reach. You notice right away, this is a right triangle. In fact, I can tell that the 12, the length of the ladder, is the hypotenuse because it's across from that right angle. So when we set it up, I'm going to use 4 as the A value, H as the B value, and 12 as the hypotenuse. So with some arithmetic, and now subtracting 16 from both sides, I find that H squared is equal to 128. I don't know what the square root of that is, so we'll just go ahead and do a decimal approximation using the calculator. Looks like H is going to be about 11.3. And this was a word problem, so it has some units attached. It's going to be 11.3 feet. The next thing we're going to look at isn't quite as familiar to most students. That's special right triangles. These are triangles that occur very often. The two most common are 45-45-90 triangles and 30-60-90. We'll start with the 45-45-90. In this triangle, there's some special relationships among the sides, mostly coming from the fact that it's an isosceles triangle. If you remember before, isosceles triangles have the same base angle. So like in this case, they both have 45 degrees. That means their sides are going to be the same. I labeled those with the letter A. Just as a quick proof and showing where that other number is coming from, let's go ahead and do the Pythagorean theorem. A squared plus the B squared, which just so happens to be the same as before, it's another A, equals C squared. So on the left-hand side, these are like terms. They're both 2A squared. What I'm trying to do is figure out exactly what the hypotenuse is equal to based on the sides that are equal to A. So I'm going to go ahead from this at this point and go ahead and take the square root of both sides. That gives me that c is equal to the square root of 2a squared. Or simplified, c is going to equal a times root 2. And this doesn't seem like a big deal, but what that's telling us is that there's a relationship between the side. You shouldn't have to do the Pythagorean theorem every time you see a 45, 45, 90 triangle. It should be really quick and easy. In fact, if you know the sides, all we do is just stick a root 2 next to that number. Let's look at the two examples down below so you can see how it works. You notice on this first example, A, the two sides across from the 45-degree angle is given as 5. So here A is 5. That means, according to this, this picture up here, the missing side, without me doing any work at all, will automatically be 5 root 2. If these sides would have been 10s, this hypotenuse would have been 10 root 2. If these sides would have been 16, the hypotenuse would have been 16 root 2. If it would have been a letter, like let's say the letter Z, this would have been Z root 2. No work to show whatsoever. The next example B is just a little different. Instead of giving you the sides, they've given you the hypotenuse. But it's pretty clear to see what's happening. In this one, the side is 6 root 2. So just think for a second, what were the sides? You should have thought about 6. If A were 6, then this would have been 6 root 2. So I want to emphasize, for these special right triangles, there shouldn't be any work at all going on. Instead, you want to set them up, draw the picture, and then look for those relationships. Let's look at the 30, 60, 90 degree triangle, right triangle next. This is a little bit more difficult to prove just because we have to start with something that's not a 30, 60, 90. So in this one, I'm going to begin with let's say an equilateral triangle. An equilateral triangle is the one where all the sides and all the angles are exactly the same. So the top is 60, this one's going to be 60, and over here 60 degrees. The sides are all going to be the same as well. My intention is to cut this triangle in half. So let me do something just for a minute, and then I'll explain why. I'm going to make each one of these sides 2A. Instead of just the letter A. Let me go ahead and cut this triangle in half. So we're just going to focus on the right-hand side of it. We now have a right triangle. This is still 60. But the top is now 30 degrees. Remember, cut it in half. This is 2A. I don't know what that middle one is. I'm going to have to give that a letter. Let me call that B. And then finally on the bottom, this is where it's going to get kind of interesting. On the left-hand side, we said that the entire base was 2A. So if we cut it in half, the bottom is just plain A. So this is the triangle that we're going to work with for the proof. In the Pythagorean theorem, a squared plus b squared has to equal this hypotenuse squared, or 2a squared. Just in simplifying a little bit on the right-hand side, a squared plus b squared equals 4a squared. I'm trying to solve for b. It's the only one that doesn't have a relationship to the letter a. So I'm going to subtract a squared from both sides. So now I'll have 3 of them on the right. By taking the square root of both sides, I now have a relationship which is a root 3. So here's the picture down below with all of the angles and corresponding sides. Across from the 30-degree angle, we have the letter A. across from the right angle, or the hypotenuse, we have 2a. And across from the 60-degree angle, we have a root 3. So we'll have to actually pay attention now to the different sides and the different angles. Let's go ahead and take a look at these different examples below, focusing on finding the letter A. So our goal is to always look for the 30-degree angle. In this case, the number 5 is across from the 30-degree angle. So that tells me that A is 5. These are probably the easiest of all the different types that we're going to do. If we know A is 5, then the hypotenuse doubles this, or 10, and across from the 60-degree angle should just put a root 3 with it. 5 root 3. So doubled on the hypotenuse, a root 3 with it across from the 60-degree angle. The next one, we're not given that angle across from that side across from the 30-degree angle. Instead, the hypotenuse is given. So if you remember, the hypotenuse side is the 2a. And if 2a was 20, then a must be 10 in this triangle. A is across from the 30 degrees, so I could just insert that in there right away. And across from the 60 degrees is always a root 3, or 10 root 3. And the last one, I'm given the angle across from the side across from 60 degrees. This one represents the a value times root 3. If that's the case, then a must be just the number 3. Somebody already attached a root 3 to it. A goes across from 30 degrees. 2a goes across from the hypotenuse, or in other words, 3 times 2. So that side will be 6. That relationship should hold up for all of the angles. So I want to emphasize again, for 45, 45, 90-degree triangles, and for 30, 60, 90 triangles, you don't want any work at all. Instead, you want to locate the a value and then fill in the triangle picture based on these special relationships among the sides.